Nearing the end of Chapter 11, Counting Methods and Probability Theory. This section is on events involving and conditional probability. Objectives: find the probability of one event and a second event occurring. Compute conditional probabilities. Independent events. Two events are independent events if the occurrence of either of them has no effect on the probability of the other. And probabilities with independent events. If A and B are independent events, then the probability of A and B equals the probability of A times the probability of B. Here's an example. A U.S. roulette wheel has 38 numbered slots, 1 through 36, 0 and 00. 18 are black, 18 are red, and 2 are green. The ball can land on any slot with equal probability. What is the probability of red occurring on 2 consecutive plays? Solution. The probability of red occurring on one play is 18 because there's 18 red out of 38. Or reducing it, we get 9/19. The probability of red and red, 2 instances of red, would be the probability of red times the probability of red, which gives us 81 over 361. And if you form that as a decimal, it's approximately 0.224. Next example, independent events in a family. If 2 or more events are independent, we can find the probability of them all occurring by multiplying the probabilities. The probability of a baby girl is 1/2, so the probability of 9 girls in a row is 1/2 used as a factor 9 times, which is shown below. When we multiply 1/2 9 times, we get 1/2 raised to the 9th power, which is 1 over 512. Example 3. If the probability that South Florida will be hit by a hurricane in any single year is 519, we want to find the probability that South Florida will be hit by a hurricane in 3 consecutive years. So the probability of hurricane and hurricane and hurricane would be the probability of a hurricane times probability of a hurricane times probability of a hurricane. Since the probability for 1 year is 5 over 19, we take 5 over 19 times 5 over 19 times 5 over 19, which is 125 over 3,859. Changing it to a decimal, we get approximately 0.018. Using the same data, now we want to find the probability that South Florida will not be hit by a hurricane in the next 10 years. So the probability of no hurricane would be 1 minus 5 over 19. Remember, we studied that in an earlier section. You take the 5/19 from 1. This would be 14 over 19, or changing it to a decimal is approximately 0.737. The probability of not being hit by a hurricane in a single year is 14 over 19. The probability of not being hit by a hurricane 10 years in a row is 14 over 19 used as a factor 10 times. So it would be 14 over 19 raised to the 10th power, which is approximately 0.047. Moving on, we're going to look at and probabilities with dependent events. 2 events are dependent if the occurrence of one of them has an effect on the probability of the other. And probabilities with dependent events. If A and B are dependent events, then the probability of A and B is the probability of A times the probability of B, given that A has occurred, because they're dependent. Here's an example. You have won a free trip to Madrid and can take 2 people with you, all expenses paid. The bad news: 10 of your cousins have appeared out of nowhere and are begging you to take them. You write each cousin's name on a card, Place the cards in a hat and select one name. Then you select a second name without replacing the first card. If 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. These are dependent events because we're not putting the names back in the hat. So the probability that they speak Spanish times the probability that they speak Spanish, given that a Spanish cousin was selected first. We've got 10 cousins. We've got 3 that speak Spanish. So the probability on the first draw that the cousins speak Spanish is 3 out of 10. That leaves only 2 cousins that speak Spanish out of 9 cousins are left. So for the second draw, it would be 2 over 9. Multiplying these together, we get 6 over 90. We have to reduce 1 over 15. Changing to a decimal by dividing, we get approximately 0.067. Now we're moving to 3 dependent events. 3 people are randomly selected, 1 person at a time, from 5 freshmen, 2 sophomores, and 4 juniors. Find the probability that the first 2 people selected are freshmen and the third is a junior. So the probability on the first draw of getting the probability of first 2 are freshmen and the third is a junior. That's what we're looking for. Probability on the first draw that one is a freshman times the probability of a freshman given a freshman was selected first times the probability of a junior given a freshman was selected first and a freshman was selected second. This corresponds with our data that we're given. So probability of freshmen, there are 5 freshmen out of 11 people. The next one, we have selected 1 freshman, that leaves 4 out of 10 people. And the third, the probability of a junior, given that a freshman was selected first and a freshman was selected second. So we've got 4 juniors. There are 9 people left. So when we multiply all these probabilities together, we get 8 over 99. Conditional probability. The probability of event B, assuming that the event A has already occurred, is called the conditional probability of B given A. This probability is denoted by probability of B over A. And of course, here's an example. A letter is randomly selected from the letters of the English alphabet. Find the probability of selecting a vowel given that the outcome is a letter that precedes H. So we're looking for the probability of a vowel, and we're given that the letter must precede H. This is the probability of a vowel if the sample space is restricted to the letters that precede H, which would be A, B, C, D, E, F. So that is S. That's our sample. We see that there are 7 possible outcomes in this sample space from the previous slide. We can select a vowel from this set in one of 2 ways. We can get an A or we can get an E. So the probability of selecting a vowel that precedes H is 2 over 7. In example 7, we're looking at conditional probabilities with real-world data. Mammography screening on 100,000 U.S. women ages 40 to 50 is shown in this table. So we have a positive mammogram, and it shows breast cancer, no breast cancer with totals. A negative one, breast cancer, no breast cancer with a total. And the last row gives the total for each column. Assuming that these numbers are representative of all women, U.S. women, age 40 to 50, find the probability that a woman in this age range has a positive mammogram, given that she does not have breast cancer. So we want the probability of positive mammogram with no cancer. There are 6,944 plus 92,256, or a total of 99,200 women without breast cancer according to the table. So the positive probability of positive mammogram, no breast cancer, would be our 6,944 over the total 99,200, which is approximately 0.07. That concludes this lesson.